Hello and welcome to the Lab 4 report for Physics 2212. So a basic introduction and preview about what we're doing in today's lab. Our purpose is to measure the distance dependence of the magnetic field due to a small bar magnet and compare our measurements to the distance dependence predicted by the equations for the on and off axis magnetic fields. And our results were that the n value equals negative 5.324 and that our mu, or our magnetic dipole moment, equals 2.472. Our fundamental principle we'll be looking at is the Biot-Savart law, which essentially says that the magnetic field is equal to the magnetic field constant, which is mu naught over 4 pi I dl sine theta over r squared. This can, of course, be then derived into all of our other equations, which we'll be using that look a little bit more familiar today, like the magnetic field for an on and off axis dipole and the magnetic field for a bar or point charge. So our basic experiment setup is that the system is the phone with the magnetometer and the surroundings are the earth and the bar magnet. Our ruler in this case was a couple sheets of paper, so not exactly the easiest setup, but it worked. And so basically we want to find the magnetic sensor in the phone first and then use the magnetometer to find distance for various values in the data chart and then find both the on-axis and perpendicular values for the magnetic field. So here's our data sheet after completing the experimentation. You can see on the top left area is all of our values for the on-axis, and then the bottom area is our off-axis field. And over here we have the magnetic field kind of graphed in an interesting way. We have it as the natural log of the magnetic field of X versus the natural log of R. And we find that our final equation for the line is y equals negative 5.3245x minus 11.727. And those values will become really important if you look on the right-hand side over here. So obviously we have our distance, which is our average off-axis field distance, or distance perpendicular, which is 0.387 meters, which is calculated again by the chart. And then our n value is going to be our slope value for that line we created on the graph, which is negative 5.3245. Our B net is also calculated by the chart and is 0.000433 Tesla. And then our ln of k can be found again with the y-intercept, which is going to be negative 11.727. Looking at the computations we did to find the magnetic dipole moment based off of those values, we kind of use the equation up top, which is the magnitude of the magnetic field of the bar equals kr, which equals mu naught over 4 pi mu over r cubed. So our k value, like we said earlier, can then be found to be 8.0728 times e to the negative 6. Our r is that distance perpendicular. Our n value is what we found before. And when you plug all of those values in, our mu value is 2.472. And we can observe overall that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction, and that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. So using all of these values, we can go ahead and set up a computer model for the off-axis magnetic field. So here we have an equation which was provided to us, which is again just a derivation of the original Biot-Savart law that was our main principle for this lab. And then we're going to maintain the perpendicular distance, 0.386, and then the mu value that we found, which is 2.472. And these are the most important sections of the coding in glow script. Here are the results of our computer model. You can see the arrows represent different pieces of the magnetic field, which is very consistent with accurate values, including in the magnitude and direction. And then if we're looking at our experimental versus computational values, you can see that our observed results or experimental results were 4.33 and our computational results were 2.4. And they're really different, and there's a couple reasons. You can include the nearby electrical equipment interference, the accidental smartphone, steel or iron, and of course, measurement error. And additional questions are, what if we hadn't oriented our experiment to compensate for magnetic north? And this would have led to inconsistent x values all over the place, which would lead to an inaccurate b net value. And our what if second one is we would expect the measurements to differ. The magnitude would double, but the direction would remain consistent as there is this superposition of magnets. Thank you.